Hello and welcome to the YouTube channel of Canara Engineering College. In this video session, we'll study regarding the ARM processor fundamentals. So in the previous video sessions, what we have done is we have covered the embedded systems with ARM processor. We have studied the details regarding what are the basic components of the embedded system hardware and embedded system software along with the design philosophy that has been adopted in the ARM processor. So in this chapter or in this video session, we'll be focusing on the processor itself. That is, we'll be focusing on the ARM processor itself. So first of all, what we are going to do is we are going to have a fundamental overview of the processor core and describe how the data will be moving between the different parts of the processor. We'll also be describing the programmer's model from a software developer's view of the ARM processor, which should be showing us the functions of the processor core and how the different parts are going to interact. And we'll also be looking into the core extensions that form the ARM processor core. That is, we'll be looking into how basically the ARM processor core or the core of the processor has been extended in order to do the multiple or in order to accommodate the multiple functionalities. So basically the core extensions are used in order to speed up and organize the main memory as well as to extend the instruction set. So at the end of the chapter, we'll be covering the revisions of the ARM core architecture by describing the ARM core naming conventions used to identify them and the chronological changes to the ARM instruction set architecture. So that is at the end, we'll be looking into all these particular things. Uh, Finally, to conclude, we'll be introducing the architecture implementations by subdividing them into specific ARM processor core families. So this is an overview of the second chapter of module 1. So the second chapter here is all about ARM processor fundamentals. So we'll be basically concentrating only on the processor, how it is going to look like, how it is going to function, maybe something with respect to the memory, maybe something with respect to the core extensions, what should be done in order to accommodate or in order to enhance the functionality of your ARM processor. So as I said you, what we are going to do in the beginning thing is, we are just going to check the programmer's model of software developer's view. So the diagram what you can see here, this is called as programmer's model of software developer. So normally a software developer is going to look into the ARM processor in this particular manner. So this is how he is going to look into. So programmer, what he can do is he can think of a ARM core, connected by data buses as it has been shown here, and the arrow marks what you can see here, this indicates the data flow between the various operational blocks or maybe between the storage areas. Also, you can check out here, this is not only about the flow of data but also the abstract contents that make up the ARM core. So when I speak about the programmer's model, the programmer will be looking into the ARM processor as it is shown here. He will be looking into the ARM core. This is your ARM core where the data is going to get processed, and these are all the memory and other functional units which will be making the data processing go with ease. Also, you can see the arrow marks which indicate the buses and the direction of the data and the instruction. So we'll start with the explanation with respect to this particular block diagram here, or we'll try to explain the programmer's model here. So normally the data and the instructions will be entering into the ARM processor core in a same bus. This particular concept has been called as von Neumann implementation of ARM, where data items and instructions are going to enter the ARM processor core using the same bus. Whereas in the context, in the Harvard implementation, the instructions and the datas are going to enter via the separate buses. So you can see here the datas are getting, you can see on the top of this, the datas are entering, or you can see here the data is entering to the ARM extension core. Data as it is being entered, it is going to be sign extended. So before it is going to get processed, please do remember the ARM processor is a 32-bit processor. It's a 32-bit processor. So whatever data it is going to enter to the ARM processor core, if it is less than 32-bit, this particular block, that is sign extend block, is going to extend the number of bits to 32-bit. For example, let us say that 8-bit data is entering into the processor. So what has to be done is, this has to be packed with zeros and you need to convert this into a 32-bit data. This particular function is being done by the sign extend block. If it is 16-bit, it has to be converted to 32-bit. So that is the work what has been done by the sign extend block, what is being seen here, or the block what is seen here is going to sign extend the data what is going to enter into the ARM processor core. If instruction is going to enter into the ARM processor core, the instruction decoder is going to decode the instruction as per the requirements of the processor core. So instruction decoder will be translating the instructions before they are actually executed. Each instruction executed belongs to a particular instruction set. It may be a arithmetic instructions, it may be a logical instructions, it may be a relational instructions, or any instructions. Whatever instructions are going to enter, they have to be decoded. Once the instructions are being entered, they will be decoded by this instruction decoder before they are actually processed. As we have explained in the very first part, that is in the design rules of the ARM or RISC design philosophy, we studied something with respect to load store architecture. If you remember, we have studied something with respect to, or the last point was load store architecture. So the ARM processor, like all the RISC processors, uses a load store architecture. So this means, so what this basically, this load store architecture means? This means that it has two instruction types for transferring the data in and out of the processor. Load instructions copy the data from the memory to the registers in the core, and conversely, the store instructions copy the data from the registers to the memory. So it means that you have a processor here and there are registers. There will be registers inside the processor. We'll look into this registers later. There are registers in this processor. So, and there will be memory in which you will be loading the data or the instructions. So the data what has been loaded in the memory, if it has to be processed, will be loaded to the registers that are present in the processor, and in order to move the data from the memory to the registers, we'll be using the load instructions. After the data has been processed in these registers, the data will be moved back to the memory, and in order to move the data back from the registers to the memory, we'll be using the load store instructions. That is what we call it as load store architecture. You need to understand the manipulation of the data is happening in the registers. It doesn't happen in the memory, it happens in the registers of the processor. It doesn't happen in the processor, it happens in the registers of the processor. So load is all about moving the data from the memory to the registers. The registers details we'll be checking out later, and store instructions is all about moving the processed or manipulated data back to the memory. So your data has been moved to the register. So this register is what I was speaking about here. So this register is the register where the data is moved. If you're asking me, sir, from where did this data come from? The data what you can see here has already come from the memory. So from the memory, data and instructions are entering into the processor core, and if the data is not 32-bit, it is sign extended, and if the instructions are decoded by the instruction decoder, and the instructions and the data are stored in the registers. After the data are stored in the registers, those data are moved to the ALU, because you want the data to be processed, right? Arithmetic and logical unit. So basically in the processor, we will be having two source registers, and those registers are named as Rn and Rm. Rn and Rm are the source registers, and there is one destination register, that is Rd. Please remember the register what we can see here, these registers are also 32-bit in size. These registers are also 32-bit in size. It is not 16-bit or 8-bit registers. The registers in which the data is getting stored before the data gets manipulated by the ALU is also 32-bit register. Also in case of your, maybe I say that if the data is not 32-bit, what happens is it gets sign extended. It will be getting sign extended, and later it will be placed in the register. As I said you, my ARM processor has got two source registers, that is Rn and Rm, and one destination register, that is Rd. So your data is in the source register right now. From the source register, you want the data to be moved on to the ALU. So the data from the source register will be moved on to the ALU. Remember, one of the source register data before getting moved on to the ALU, it passes through the barrel shifter. We have studied about this barrel shifter when we studied regarding the instructions of the ARM processor, or risk design philosophy. When we studied regarding the 32-bit instructions. So there is something called as barrel shifter. So one of the data will be getting shifted if required as per the requirement by this barrel shifter, and that process is called as pre-processing of the data. That process is called as pre-processing of the data. So pre-processing of the data is done in the barrel shifter, and the data A and B from the source register will be entering into the ALU. Once they enter into the ALU, my arithmetic and logical unit will be doing the arithmetic and logical operations if it is arithmetic and logical operations. If it is multiply and accumulate instructions, if it is all about multiplication instructions, the data will be moved on to the MAC. The output of this ALU and MAC will be moved on to the destination register. You can see there is an arrow mark which is pointing back to the destination register. So your data Rn and Rm has come to the ALU. The data processing has taken place. From this data processing block, the data has moved back to the destination register. Based on the instruction what comes inside, whether it is arithmetic and logical instructions or whether it is multiply and accumulate instructions, the data will be moved on to the ALU or into the MAC. Once the data has been processed, it will be moved back to the destination register. From the destination register, it will be moved back to the memory. It will be moved back to the memory from where it has to be stored. Let's say my first data is stored here. After that, the second data will come inside and they will get processed. So where should my second data should get stored? My second data should get stored in the second location. Let's say the address of this memory location is 1, address of this memory location is 2, this is 3, this is 4, and this is 5, right? Now, if the first process data is getting stored in the first memory, the next process data should get stored in the second memory location, right? Always, if the data comes and gets stored in the first memory location itself, the first data is gone. So you can see here, after the ALU, there is an address register. So this address register will give the address of the next memory location where the next data has to be stored. And you can see there is an increment. There is an incrementer here. So let's say that my first data 1 has been produced and it goes to the register, and from here it goes to the memory. After that, let's say data 2 comes. When data 2 comes, this incrementer will increment the address here, so that my pointer will be pointing to the next memory location, so that my data 2 will go to the register RD. From register RD, it will be going back to the second memory location. That is why you can see there is an incrementer here. So the address register is all about containing the address of the memory location where the data has to be stored. After the first memory location has been occupied, the incrementer will be incrementing the address of this address register, so that my second data can go and get loaded in the second. My third data will go and get loaded in the third memory location. Fourth will get loaded in the fourth one. If the incrementer was not there, all my data will come and get stored in the first memory location itself. So I don't want this to happen. That is why we have an incrementer and an address register which has been connected here. Other than that, what additional things what you can see is, uh, after passing through the functional units, that is after passing through this particular ALU and MAC, RD is returned back to the register file using the result bus. So the bus what you can see here, this is called as result bus. From the result bus, from the destination register, it is copied back to the memory location using store instruction. This is all about programmer's model. Programmer model explains you how the data and instruction will be flowing to the ARM processor core, and from the ARM processor core, how the manipulated data or the processed data will be moving back to the memory location. This is all about your programmer's model. As I said you, there are some registers here. It is now time for check out how many registers are present here, what is the size of the register, how do they actually look like. It is time for us to look into those particular registers. So let us look into those particular registers here. This is all about the explanations what I have been given to you, or what I have been giving to you in the previous slide. See here, the instruction decoder translates the instruction. The ARM processor, like the RISC processor, uses load store architecture. After that, data processing instructions. After that, what are the registers files available? What are the destination registers and source registers? And what will be the arithmetic and logical unit be doing? And what will be the load and store instructions doing after the data has been manipulated? Later, the manipulated data will be moving back to the destination register via the result bus, and from the destination register, it will move back to the memory location. After the first memory location has been filled up, the incrementer will be updating the address of the next memory location in the address register, so that my data can go back to the next immediate memory location. The processor will be continuing to process the data until it receives an exception or it receives an interrupt. Let's check out what is this interrupt and exceptions later. So it's time for us right now to check regarding the registers that are present in the ARM processor core. So if you say this is your ARM processor core, you will find registers here. So you need to kindly understand that the data what has come from the memory locations, will be stored in this particular registers. This is your memory. And the data manipulating instructions will be operating on the data on this registers. Please understand, data from this registers will not go to the processor. The processor will manipulate the data in this registers directly based on the data manipulating instructions. Now it is time for us to check out how these registers are going to look like, and what is the size of this register, how many registers are present, what are the names that are given to the registers, are they general purpose registers or are they specific purpose registers. All these details has to be checked. So let's check them up right now. So general purpose registers hold either data or an address. So the data from the memory and the instructions from the memory will be loaded in the general purpose registers. They are identified with the letter R. You can see the registers that are identified: R0, R1, R2, R3, R4, R5, R6, R7, R8, R9, R10, R11, R12, R13, R14, R15, CPSR, and one more is present here. This is actually named as SPSR. So these are all the registers. Every register has been named with the prefix R. So all these registers are 32-bit registers. So your data A will come here, data B will come here. Processor will be working on this particular registers, and A plus B will be stored in the R0 register, and using the store instruction you can move back this data to the memory. So this is how your registers are going to look like. So how many registers do you have here? R0 to R15. So basically you have got 16 registers. And all the registers are 32-bit registers. Out of this 16 registers, R0 to R12, these are general purpose registers. General purpose registers means you can use those registers to store the data or to store the instructions. You can use them for anything. See here, figure shows the active registers available in the user mode. We'll check out what is this user mode later, because there are 7 different modes in which your processor is going to work. We'll check regarding this modes later. Protected mode is normally used when executing applications. We'll check regarding the protected mode also. Right now what we'll remember is there are 16 registers and all are 32-bit registers. Out of 16 registers, 13 are general purpose registers and 3 are special purpose registers. The processor can operate in 7 different modes, which we are going to study very shortly. We are going to look into the very different or 7 different modes in which your processor is going to work. There are up to 18 active 32-bit registers. So 16 here plus 2. So total it is 18 active, 32-bit registers that are available, out of which 16 data registers and 2 processor status registers. So CPSR means, here CPSR means it is current program status register. SPSR means it is given by the name SPSR. We actually do not use it in the normal modes. So these are the status registers that is available. Current program status registers is very commonly used by your ARM processor. So the data registers visible to the programmer are R0 and R15. So let's check out regarding this particular registers that are available. So you would have seen there R13, R14, R15 has been shaded and they have named as SP, LR and PC. SP stands for stack pointer, LR stands for link register, PC stands for program counter. Okay. So out of the 16 general purpose register, R13, R14 and R15 has got a specific purpose. So I cannot call them as a general purpose. If you are not using these registers for that particular specific purpose, I can use it as a general purpose. So R13, R14 and R15 are specific purpose registers and the purpose is given here. Register R13 is traditionally used as a stack pointer and stores the head of the stack in the current processor mode. So why do we use stack here? Let's say this is your stack. So let us say that this is your processor and this is your register. The data in this register is getting processed, okay? Suddenly you get an interrupt. Once you get an interrupt, your program will stop the execution of this particular data and it will jump to next part of the register. So what should happen is, I want this particular data to be stored somewhere. That data can be stored in the stack, and in the stack it will always be last in first out, right? So I'll be storing the data here, and the memory location where you have stored the data last has to be remembered. This address has to be remembered. This address is actually remembered by your register R13. That is what is your stack pointer register. R14 is your link register. Link register is a register where the core puts the return address whenever it calls a subroutine. So let's say that my processor is executing a program, and it is executing this particular line. So all of the sudden there is a subroutine, or it has to jump to some small program. And execute it, some micro program and execute it. After the micro program is executed, it has to return back and it has to execute this particular line, right? So this particular address or the address of this particular instruction will be stored in the link register. So that address will be stored in the register R14. So specific purpose. R15 is a program counter. Program counter is a register which contains the address of the next instruction to be fetched by the processor. So you have got multiple instructions. This many instructions are being covered up. So this is the next instruction what is to be fetched. This will have an address. So your register R15 or the program counter will be containing the address of the next instruction which has to be fetched by the processor. Suppose if you are not using it as a stack pointer, link register or program counter, I can store my data and instructions in R13, R14 and R15. But as far as possible, I will not be using that R13, R14 and R15. as general purpose, using them as a specific purpose itself, because you are not pretty sure when you are going to get an interrupt. You do not know when your program has to jump to a subroutine. Subroutine means a main program. In between, you do not find some data. In order to get the data, you go to some other program, get the data and come back. That is, this program is called as subroutine. So you do not know at what point you need to be jumping to the subroutine. Also, R15 should be holding the address of the next instruction, right? Because you need to know what instruction has to be executed next. So R15 is going to hold the address. So there are generally 16 general purpose registers, out of which only 13 are available, remaining 3 are specific purpose: stack pointer, link register and program counter. Other than that, there are 2 more registers which are available in the ARM processor, and that has been named as CPSR and SPSR. CPSR is current program status register, which we are going to check. Other one is SPSR, saved program status register. So after you execute a particular instruction, every instructions are conditionally executed. So after every instruction is executed, you need to go and check the current program status. If the program status is as per the indicated, then only the next instruction can be executed. Always you cannot execute the next instruction. That is why we have something called as CPSR here. CPSR, which will be giving you the status of the next instruction. That is what is your CPSR. SPSR is all about saved program status register, which generally don't tend to be that important as that of your CPSR. So saved program register, as I said you, when you are jumping from the main program to the sub program, a part of the program has to be saved somewhere and status has to be saved, right? So that has been indicated by your saved program status register. So this is regarding your registers. I said you there are registers, data will be moving from memory to the registers. So there are generally 16 plus 2, that is 18, 32-bit registers in your ARM processor core. Now what we'll check out is, we'll check out what is the CPSR actually going to look like, or how is the CPSR actually going to look like. So the CPSR is basically a 32-bit register. It is a 32-bit register. So this particular register is used to monitor and control internal operations. As I said you, every instruction is conditionally executable. After a particular instruction is executed, only then the next instruction is going to be executed based on the condition. If the condition is not satisfied, next instruction is not going to be executed, your program is going to stop. So the conditions will be checked in this particular CPSR, or current program status register. The CPSR is a dedicated 32-bit registers and resides in the register file. Figure shows you, this particular figure shows you the CPSR. You can check out here, it's a 32-bit, so 4 bits are here, here there are around 8 bits. So 4 bits are conditional flags. This is negative flag, 0 flag, carry flag, parity flag. So it's not a parity flag, it is overflow flag. Fine. Other than that, there is one more field which is called as control field. In control field, there is something called as interrupt mask, thumb state, processor modes. I said there are 7 modes, right? Those particular things will depend how it is. If it is 0000 or 000, it is one mode. If it is 0001, it is one more mode. If it is 0010, it is one more mode. So there are 7 modes in which your processor is going to work depending on the bits that are stored here. So this is your CPSR. In addition to this, what happens is, okay, let's get in detail. It basically has around 4 fields. One is called as flag field, one is status field, extension field, and control field. Status field and extension field are preserved for the future. They are not going to use it. As of now, they are not going to use it. Who knows? In future, they might use it. Flag field, out of flag field, I am going to use 4 fields. That is negative flag, 0 flag, carry flag, and overload flag. and if you want you can use saturated flag also. Normally I do not use it. So based on the status of this particular conditional flags, your instructions will get executed. Similarly, there is something called as interrupt mask fields here. So it is I and F. If I is equal to 1 and if F is equal to 0, whatever interrupt comes, it is denied. If I is equal to 0 and if F is equal to 1, whatever interrupt comes, it is going to be serviced. Next is thumb state. If thumb state is made 1, you write an 8-bit instruction or 32-bit instruction, whatever instruction you are going to write, it is going to get converted into a 16-bit instruction. That is what is a thumb state. Mode state it is explained here. See if the modes has been given here, which we are going to check here. For your curiosity, if you want to know what are the different 7 modes in which it is going to work, one is user mode, system mode, first interrupt request mode, supervisor mode, abort mode, and undefined mode. So these are the 7 modes in which it is going to work. We'll check this particular modes in detail. In addition to this, there is one more bit which is being used by this particular flag, which is called as jazzle bit. This jazzle bit, if it is enabled, if this jazzle bit is enabled, all the instructions are going to get converted into 8-bit instructions. All the codes are going to get converted into a 8-bit codes. So this is what is your CPSR all about. After a particular instruction is executed, you need to come and check here whether ALU or arithmetic operation has generated a negative number, whether it has generated a 0 flag, or whether it has generated a carry, whether an overflow has been generated, or looking into this particular values, you can check out whether interrupt, if I give any interrupt, whether interrupts is going to be masked or whether it is going to be allowed, whether thumb mode is enabled or whether jazzle bit has been or jazzle mode has been enabled, or you can also check in which mode it is going to work. This is regarding your CPSR of your ARM processor. So we will wind up for the CPSR right now. In the next video session, we will discuss regarding the various modes in which the processor can work. Thank you.